Hello guys, welcome to the video. In this particular video we are going to see the working of a simple air cooling system which is used in the aircraft, and basically this system is used to cool the passenger cabin. Okay, so let us see how it works, basically what are the various components of it. And in this particular video, the last part will be the temperature entropy diagram for this particular simple air cooling system. We'll go one by one. So let us understand first the construction of the system over here. Here there is one chamber provided. This is the chamber. Okay, and in this chamber you'll have the compressor, turbine and the ramming section. Then you'll have the heat exchanger over here. This is the heat exchanger. Then this is the cooling turbine. Fine. And there is one combustion chamber is provided. Basically these particular components, gas turbine, combustion chamber and main compressor, are the gas turbine cycles which are used in the aircraft for the propulsion purpose. Okay, so this is the part of propulsion system. However, we are using the main compressor for cooling over here, for the cooling purpose over here as well. So in this particular case, actually the aircraft is moving in the rightward direction, in this particular direction, which I have shown the arrow over here. That is the direction of aircraft. This is the direction of aircraft, and this is basically an open system. So atmospheric air will be used as a refrigerant over here. And this is not our regular air conditioning system where we are using the vapor compression system and the refrigerant will be there and which will be the closed system. This is not like that. And the reason behind is to reduce the weight of the system, because whenever we are designing the aircrafts, the main criteria or the main issue over there is the weight of system. Okay, so to reduce the weight, whatever existing part of the system available with the aircraft, that parts are used over here. Fine. So I'll just explain the system over here, how it works basically. So the ambient air initially comes into the ramming section. Okay, so this is the ramming section. Ram air is not the different air than the ambient air, it's the ambient air only, but here we'll have some conversion type of section, something like this. Okay, it is something like this. I'll just draw this particular diagram so it will understand better. Okay, so this is the something section like this. So here you'll find there is the reduced area, and because of this reduction in area the air get compressed. Okay, so this particular is the partial compression. The ramming is nothing but the partial compression, and that air is further passed to the main compressor over here. So in the main compressor, the pressure and temperature of the air is getting increased. We know that the compressor are used to increase the pressure and temperature, where isentropic compression, ideally the isentropic compression will be taking place over here. So in the compressor, air will get compressed, its temperature and pressure will get increased. So that high pressure and high temperature air will be passed to the heat exchanger over here. It will be passed to the heat exchanger over here. So in the heat exchanger, basically whatever heat is there in the air, refrigerant air, that heat will get removed. Okay, and to take that heat from the refrigerant air, basically the ram air is passed over this particular refrigerant air. Okay, so if you see carefully, let's say this particular ram air will have some temperature, and that temperature definitely is less than the temperature of the compressed air. Okay, so ram air will have the temperature less than the compressed air. So here there is the compressed air. The air which is flowing through this particular line is nothing but the compressed air, whereas the air which is passing over this particular pipeline is nothing but the ram air. The ram air is having lower temperature than the compressed air, so obviously the heat will get transferred from the compressed air to the ram air. Okay, and that is how the air will get cooled over here. Now that cooled air will be supplied to the cooling turbine. So this is the cooling turbine basically. So in the cooling turbine, the air will get expanded. Okay, air will get expanded. Now we know that because of the expansion of the air, the pressure and temperature will be reduced. Okay, the pressure will be reduced, temperature will be reduced. That pressure will be reduced up to the cabin pressure most of the time. Whatever pressure is getting reduced in the turbine will be up to the cabin pressure, or the pressure is to be maintained inside the cabin. Okay, up to that it will be reduced, and as well as the temperature also will be reduced as per the requirement of temperature inside the cabin. Okay, so that is how the air will get expanded, and that expanded air, that is low pressure low temperature air, will be further passed to the cabin over here. So this is the cabin, this is the cabin part basically. Okay, and that is different than the differentiating than this particular cooling turbine section. So cabin is the different part, or which is not shown. Basically it is just shown that the air is going to the cabin. Fine. So this is how this particular system will be working. So the air which is passed to the cabin will have the temperature and pressure which are required by the passengers. Okay, now here you can see there is one component shown, which is nothing but the cooling air fan. So this is the fan provided, and here it is written as a 2 atmosphere. Basically what is the use, the purpose of this particular fan? To draw the ram air from the heat exchanger, because on its own the ram air can't flow, na? So for that purpose, to draw this particular ram air over the heat exchanger, this particular cooling fan will be provided. So there is a suction on this particular side, okay, back side of this fan there is a suction, and this is the axial flow fan which will be pumping the ram air to the atmosphere. Okay, so obviously the ram air will be passing over this particular heat exchanger in this particular fashion. Okay, and that air will be then further given to the atmosphere, as well as the compressed air, or the main air which is coming from the main compressor, which is given to the this particular cooling turbine. Also we can call this as the refrigerant air. That refrigerant will go to the cabin, and from cabin it will be again exhausted to the atmosphere. And that's why I said this is nothing but the open system. Okay, the refrigerant air is not taken back over here, it is exhausted to the atmosphere. Okay, so these are what some components and the cycle, how it works basically. So basically the temperature pressure will be increased, and then at a constant pressure you will have the heat exchange process over here, and then the air will pass to the cooling turbine, where the pressure and temperature will be reduced, which is as per the requirement of the cabin. Okay, and this particular processes will happen. I'll just explain one by one. Now the ramming section, or the ramming process will be isentropic. Then the process which happens in the main compressor, again it's isentropic, where the pressure and temperature will increase. Then air will go to this particular heat exchanger, where the heat exchange between the compressed air or the refrigerant air and the ram air will take place. So this entire process of the heat exchange will be at the constant pressure. Then that air will be given to the cooling turbine, where the pressure and temperature will be reduced, and that low pressure low temperature air will be further given to the cabin. Okay, so this is how it will work basically. Now we'll have the question about this particular combustion chamber and this gas turbine. See, this, as I said earlier, this gas turbine combustion chamber is the gas turbine cycle part, and these are used for the propulsion purpose. Basically we are using some part of work of the main compressor for the cooling purpose over here. Okay, so this is basically, this is not especially provided for the cooling purpose, this is provided for the gas turbine cycle. However, we are using some part of this particular compressor for the cooling purpose. Fine. So these are what the components of the system and the working of each component. Fine. Now what we'll do, we'll try to draw the TS diagram of this, that is temperature entropy diagram. Initially I will draw the ideal cycle, and then I will explain the actual cycle as well. Fine. So for that, what I will do, I will mark the point over here wherever the state of air is going to get changed. When I am saying the state, it is nothing but its pressure or temperature is going to get changed. Fine. Accordingly I will go on marking the points over here. So assume that I am marking the ambient air as the point number 1. I'll mark this as the point number 1. Fine, that is the ambient air, because I need these points to draw the TS diagram. So ambient air I am marking as the point number 1. Now that air is going to the ramming section. So in the ramming section, obviously the state is going to get changed, because there is the compression happening because of this particular reduced area. So the state of air will change from 1 to, let's say, 2. It will be the state 2. Now this ram air will be given to the main compressor. So in the main compressor again there is an increase in the pressure and temperature. So at the exit of main compressor, that is, let's say at this particular point I am saying, at this particular point the state of air is going to get changed, which is nothing but the exit of compressor. I'll mark that point as 3. I'll mark this as the point 3. Now the same air which is at the state 3 will be passing over here, okay, it is coming over here. So inlet of heat exchanger again point number 3 only, because there is no change in the state between the exit of compressor and inlet of heat exchanger. Fine. Now during the heat exchange process, the heat is getting exchanged between the compressed air and the ram air which is flowing over it, will takes place at the constant pressure, However, because of the heat exchange between the compressed air and the ram air, the temperature of air, that is the compressed air or the refrigerant air, is going to get changed. Okay, so obviously at the exit of this particular heat exchanger, state is going to get changed for the compressed air, and that state I'll mark as the point number 4 over here. Okay, now that air which is at the point number 4 will be given to the cooling turbine. Okay, will be given to the cooling turbine. Now you know that in the cooling turbine the pressure and temperature of air will get reduced. Okay, it will get reduced, and because of that, at the inlet of cooling turbine you have the same point, that is nothing but the point number 4 only, because the exit of heat exchanger will be given to the inlet of this particular cooling turbine. However, the exit of cooling turbine will have the different state from the state number 4, because at the state number 4 the pressure and temperature is high. If you see the air which is compressed in the main compressor, at that pressure only the air is supplied to the heat exchanger, and in the heat exchanger the pressure is going to remain the same. So in the heat exchanger the pressure will be on the higher side, whereas temperature at the exit of heat exchanger will be reduced, that is for sure. However, that high pressure air will be given to the cooling turbine, and in the cooling turbine the air will get expanded, and because of the expansion, at the exit of cooling turbine, somewhere over here at the exit of cooling turbine, the pressure of air will be reduced, temperature also will reduce, so the state is going to get changed over here. That is the I am marking as the state number 5. Now at state number 5 the air will be supplied to the cabin. Now we need to understand whether the state of this particular cabin will be different than the number 5, or will it be the same. Okay, for that I'll just explain over here. See, you have the cabin or you have the room, let's say something like this. Okay, this is the room which I am supposed to cool. Okay, now imagine that the air is coming from the cooling turbine. So this is the cooling turbine from where the air is coming. Okay, and this is the cabin, okay, which I maintain to be cooled. Okay, now assume that I am maintaining the temperature as a 25 degrees Celsius over here, and obviously there are people sitting inside it, there are lights, so continuously there will be the increase in the heat inside the cabin. Okay, these are the factors which will be adding heat to the cabin, and it's a enclosed space, so heat can't flow outside, it will be get added inside the room itself, and that is because of the internal factors like human being is there, lights are there, surrounding temperature, because of that the heat will flow inside. Likewise, there are many reasons, because of that heat will go on increasing over here. Okay, but however I want to maintain the cabin is to be at the 25 degrees Celsius. In such cases, if I want to maintain the cabin at 25 degrees Celsius, and whenever I am saying that there is the heat is getting added, so if suppose if I am not removing the heat from the room, if I do not remove the heat from the room and heat is getting added continuously, in that case the cabin can't be maintained at 25 degrees Celsius. However, the temperature of cabin will go on increasing. Correct, and that is the reason I need to remove the heat from this particular cabin. And to remove the heat, the cooling air will be supplied from the cooling turbine over here. Okay, so this is what the cooling air which is coming in, and I will be exhausting the room air outside after absorbing the heat over here. So generally what happens, the air which is coming from the cooling turbine will be supplied over here. This air, this particular air will be absorbing the heat from this particular room. It will absorb the heat from the room, and then after absorbing the heat, this particular air will be exhausted to the atmosphere. It will be given to the atmosphere. Now here one thing is need to be noted, that is the temperature of the air which is supplied to the cabin. Let's say if I maintain, if I supply the air at, let's say 25 degrees Celsius only, if I am supplying the air at 25 degrees Celsius, just imagine that the air which is supplied at supplied at a temperature of 25, and I want to maintain the cabin at a 25, and continuously there is the heat added. So will it be possible to maintain the room at 25 degrees Celsius if I supply the air at 25? Definitely not, because it will not absorb the heat from the room. Okay, though it is absorbing the heat, the temperature of the room will go on increasing above 25 degrees Celsius. So it is for sure that whatever air I am supplying over here to the cabin has to have the temperature less than 25. So it should be less than 25. Okay, it should be less than 25. Whatever air I am supplying, it should be less than 25. Assume that I am supplying air at, let's say, 18 degrees Celsius. I am supplying air at 80 degrees Celsius. Now just see, if I am supplying the air at 18 degrees Celsius, it will absorb the heat from surrounding air, and because of the absorption of the heat from the surrounding air in the cabin, the temperature of the air which is supplied over here will go on increasing, and up to what it will increase up to, it will increase up to 25 degrees Celsius, and at 25 degrees Celsius I will exhaust that particular air to the atmosphere. Okay, this is how basically it will work inside the cabin. So in such cases, the cooling air which is coming from the turbine, I am supplying at 18 degrees Celsius, where the cabin is at 25 degrees Celsius. So from here you can get that the state or the condition of the air after cooling turbine and in the cabin, both are different, correct? So after this particular cooling turbine, the state is 18 degrees Celsius, where inside the room it is 25 degrees Celsius. So I need to mark a separate point for the cabin over here. So that is I am marking as the point number 6. That is I am marking as the point number 6. Fine. Now we will try to draw the TS diagram. Now it's very easy for you to draw the TS diagram over here. Fine. I'll just erase this first of all. Okay, on the same what you can say, the slide, I will show you everything, because if I change the slide then it will be confusing for you. Okay, fine. So now we will try to draw the TS diagram. We will try to draw the TS diagram. So whenever you are drawing the TS diagram, so this is temperature, and here I am having the entropy. Okay, so it will be denoted by S, it will be denoted by temperature T. Okay, now whenever you need to draw the TS diagram, you should understand at what points the pressure is going to get changed. Okay, so I need to draw first for the pressure line. So if I draw the pressure line, it will be better for me, or it will be easy for me to draw the TS diagram. Okay, so starting with the point number 1. So I know that the point number 1 is at the ambient condition. So obviously the ambient will have some pressure. So this is the line I am showing for the ambient pressure. This is, let's say, the ambient pressure line. This is the ambient pressure line. Now that air will be going to the ramming section, and we know that in the ramming section the partial compression will take place, and because of that the pressure of this particular air will go on increasing. So that pressure will be different than the atmospheric pressure. So I will be marking this as the ram pressure over here. This is the ramming pressure. Fine. Now that ram air will be given to the main compressor. So in the main compressor, again the pressure of air will be increased. Okay, it will be increased in the main compressor. So I can say that this is the main compressor pressure line, which will be the highest pressure over here. Main compressor pressure line. Okay, this is the main compressor pressure line. Now the air is supplied to the heat exchanger. So in the heat exchanger, I already said the process is taking place at the constant temperature. So whatever the heat exchange process will be done, it will be across this particular main compressor pressure line. So need not to draw any pressure line for the heat exchanger. Now fine, now that air will be given to the cooling turbine. Here you see that the air will be expanded in the cooling turbine, and because of the expansion, the temperature of this particular rather the pressure of the cooling air, or the pressure of this particular air will be decreased over here, and that pressure I'll be maintaining, or I will have this particular pressure mostly equal to the cabin pressure. Okay, so whatever air is expanded in the cooling turbine, it will be expanded, let's say, up to the cabin pressure. So I'll be having one more pressure line over here, something like this. Okay, and this I can mention as the cabin pressure. This I can mention as the cabin pressure. Fine. So fine. Now need not to draw any line for the pressure. So all the pressure lines we have already drawn. Now we'll just go on plotting the various points over here, because we have total 6 points. Now we'll see how to plot those points. So starting with this is the, let's say, cooling process. So I will start from the right hand side. So the ambient pressure, that is the point number 1. So point number 1 will be definitely on the ambient pressure line. So somewhere over here I am showing the point number 1. So let's say this is the point number 1. Then that particular air will be partially compressed in the ramming section. So on the ram pressure line I will be having the point number 2, and we know that the process from 1 to 2, that is ambient air to ram air, it's a isentropic process or isentropic compression. So when I am saying isentropic, it means that the entropy will remain constant, and when the entropy remains constant, I will have a straight vertical line from the point number 1 to point number 2 over here up to the ram pressure line. So this is the point number 2. Okay, I am drawing the ideal cycle. Understand this first, then we will go for the actual cycle. Fine. Now from point number 2, the air will be further compressed up to the main compressor pressure line. Again, this particular process is the isentropic process from the point number 2 to point number 3. So I will be having again a straight line from point number 2. I will be having the straight line from point number 2 up to the point number 3 over here. Okay, which is nothing but the point on the main compressor pressure line. Fine. Now at point number 3, the air will be supplied to the heat exchanger. You see over here, this is the heat exchanger. Now in the heat exchange, the process is taking place at a constant pressure. Okay, it is taking place at the constant pressure. However, when the air is flowing through the heat exchanger, the temperature of air is getting reduced along that particular constant pressure line. So if you see, this is the point number 3. Along this pressure, I will be having decreased in the temperature. So somewhere over here, I will be having the point number 4, let's say. Okay, this is the point number 4. Fine. Now I'll just mark the processes over here. 1 to 2, that is the ramming process. I will write the ramming process over here. Then 2 to 3 is the compression. So I'll be writing the compressor or the compression, the main compressor. Then 3 to 4 is the process which is taking place in the heat exchanger. So I'll be writing the HE, which is nothing but the heat exchanger. Now fine. Now from 4 or at point 4, the air will be supplied to the cabin. From 4 up to 5, there is the expansion of air is taking place up to the cabin pressure. Up to the cabin pressure or the cooling turbine exit pressure. This cabin pressure or cooling turbine exit pressure, one and the same. Fine. So you will have the expansion over here. Now we know that the expansion is nothing but the isentropic expansion only in the turbines. So for isentropic expansion, I will draw a straight vertical line from point number 4 over here, something like this. Okay, so up to the cabin pressure line, this is the cabin pressure line or the cooling turbine pressure, cooling turbine exit pressure. Up to this pressure, I will be having the expansion, and which is nothing but the isentropic. So I will mark this as the point number 5. I will mark this as the point number 5, which is the turbine exit point. Now when the air is supplied to the room, it will be supplied to the room at the cabin pressure only. Now we know that when the air is going to the room, as I said earlier, you are supplying the air at 18 degrees Celsius. Okay, this is 18, whereas room is maintained at 25 degrees Celsius. So obviously what will happen with the temperature of this particular air? It will be increasing from 18 to 25. So on the same pressure line on the cabin, because the pressure is going to remain same, however the temperature is going to get increased. So on the same pressure line, you will have the somewhere over here towards increased temperature, I will have the cabin point, that is point number 6. This is the point number 6. Okay, now between the process 5 to 6, so this is the point number 5 where the air is supplied to the room and cabin is maintained at condition number 6. So between 5 to 6, the heat is getting absorbed from the room over here. It will be getting absorbed from the room. over here by the air, which is nothing but the refrigerant air. Okay, so this air will be responsible to absorb the heat from the room, and then that refrigerant air will be exhausted to the atmosphere. So whenever there is the heat absorption, we can call this as the cooling produced or the refrigerating effect produced. It will be the refrigerating effect. Okay, refrigerating effect produced, we can say. Okay, and that I can denote on the TS diagram as RE. So from point number 5 to point number 6, it's a refrigerating effect produced. Okay, so this is how actually the cycle will work. So this is nothing but the turbine. I can write this, instead of expansion I will write the turbine, cooling turbine. Okay, so now you see 1 to 2, that is the ramming, which is nothing but the isentropic. 2 to 3 is nothing but the isentropic compression. 3 to 4 is nothing but the heat exchange process in the heat exchanger. 4 to 5 is nothing but the expansion in the cooling turbine, and 5 to 6 is nothing but the refrigerating effect produced over here. Okay, so this is basically the ideal cycle. Now whenever the efficiency for the compressors are mentioned and the turbines are mentioned, we supposed to draw the what you can say, the actual cycle. In some cases the ramming efficiency is also set. Fine, so in that case, if the ramming efficiency is set, then how the diagram is to be drawn, that I will show you. Fine, so in that case, so what I will do, I will just erase this particular diagram, and then we will draw one more diagram over here. That is the TS diagram only, but that is for the actual cycle. That will be for the actual cycle. Fine. So this is how you can draw the ideal cycle, and whenever the efficiencies for compressor and turbines are not mentioned, then need not to draw the actual cycle. You can go with the ideal cycle only. Fine. Okay, this is what the temperature axis. Then I'll have the, I'll just go on drawing the pressure line. This is the ambient pressure, ram pressure, main compressor pressure. Okay, so ambient, ram pressure, main compressor pressure, and we'll have the cabin pressure as well. This is the cabin pressure. Fine. Now what I will do, I will assume that there are losses in the ramming process, in the main compressor process, and in the turbine process. Okay, so assume that if there is the loss in the ramming process, I will have the ramming exit pressure line somewhere over here. This is the actual ramming pressure line, actual ram pressure line. This is the actual ram pressure line. Assume that this is the actual ram pressure line. So in this case, what happens basically, ideally I used to draw, this is the point number 1, obviously, which will be on the ambient line. 1 to 2 I used to have the isentropic process. 1 to 2 I used to have the isentropic process, but because of the losses in the ramming, this particular point 2 will be shifting on the actual ram pressure line, and that particular point 2 will be having the same temperature as of the ideal cycle. Okay, so here I'll be having the point number 2 dash. This is the point number 2 dash. See, this particular temperature at point 2 is known to be the stagnation temperature, because this is the ramming section, and in the ramming ideally maximum temperature will be limited. Beyond that the temperature can't be increased, and that's why though there is the loss in the pressure, the temperature will go up to the maximum temperature which is achieved in the ideal process, and hence you will not have the 2 dash point separately on the increased side. Okay, so this will be equal to the 2 only. So 2 and 2 dash will be the same. The temperature at point number 2 and temperature at point number 2 dash will be the same, and the actual ramming will be from 1 to 2 dash. So this is the actual ramming. Now what I will do, I will have the next process from ramming, so that is nothing but the main compressor process. So ideally I will have the process from 2 dash to 3. Okay, if I consider only the loss in the ramming. However, there is the loss in the compressor because of the friction. Okay, so because of the frictional losses, this particular point 3 will be shifted to the new point, and the new point will have the higher temperature than the point number 3, because in the compressor the maximum pressure will be limited. Because the compressors will work in the fixed compression ratios, correct now? So the maximum pressure will be limited. So in that case, if the maximum pressure is limited and if there are the losses, that is nothing but the frictional losses, then in that case the temperature of air at the exit will increase, and which will be higher than the point number 3. So I'll be having the on the same pressure line, because I'm saying the pressure is not going to change because compression ratio is same. So on the same pressure line, I'll somewhere on the right hand side I'll have the new point, which is nothing but the 3 dash. So from point number 2 dash to 3 dash is nothing but the actual compression. So 2 dash to 3 dash is the actual compression. Now in this particular case, I am assuming that there is no any pressure drop in the heat exchange process. So I'll be having point number 4 on the same pressure line. Okay, let's say there is no any pressure drop at this particular moment of time. From 4, the process happens in the cooling turbine, which is nothing but the expansion process up to the turbine exit pressure or the cabin pressure. Fine. So this is the isentropic process. However, again the turbines are working in the fixed expansion ratios, and there are again the frictional losses. Because of this frictional losses, the temperature at the exit of the turbine will be higher than the ideal temperature at the exit of turbine. So the actual temperature or the actual point will be somewhere over here, okay, which will be on the higher side than the point number 5. I will mark this as the 5 dash, and the actual process will be starting from 4 dash to 5 dash, okay. Whereas I'll be having the point number 6, which is the fixed one, which it will not change. So in this actual cycle, if you go by, you will have the refrigerating effect from the 5 dash to 6. It will be from 5 dash to 6, okay. So this won't be from 5 to 6, it will be from 5 dash to 6. So whenever you are dealing with the actual things, they will mention the efficiency for the compressor and the expansion and the ramming as well. So whenever they are mentioning in the numericals, see, whenever it is mentioned that the efficiencies are given for ramming, compressor and the expansion device turbine, then and then only you are supposed to go with this particular actual process. Otherwise it is not required at all to show the actual points. Fine. So please note this, it's very important. Okay, so in some cases the ramming efficiency won't be given, however the compressor and turbine efficiency will be given. So in that case the process, if assume that the ramming efficiency is not given, so in that case the main compressor process will start from the 2 only, point number 2 only, instead of 2 dash. Okay, need not to show this particular actual 2 dash point. Okay, so take care of that if the ramming efficiency is not given. If the ramming efficiency is given, then definitely you have to show this particular point. Fine. So this is what about the simple air cooling cycle and its TS diagram. So in the next video, what we will do, we'll see the COP of this particular system, how to find out the COP of the system. Fine. So I hope you understood this particular cycle, and just go through the video carefully, you will definitely understand. Thank you.